Okay, good afternoon. Welcome to Emergent States of Matter, February the 15th, 2021. And today what we're going to talk about is helium. So this is section 1 in my notes. And so what we're going to do is just quickly go through some of the basic properties and then try to, as quickly as possible, get into a discussion of off-diagonal long-range order and things like that. So here is our goal. Well, I want to cover the basic aspects of the helium phase diagram. Then I want to very quickly get onto a quantification of what superfluidity is in terms of elementary fluid mechanics. And then I want to get into a quantification of types of quantum order. And so in particular, what we'll be talking about is off-diagonal long-range order, OD-LRO, and that was going to lead us into a discussion of the topological defects in superfluids. So that's roughly where we're going for a bit. So in terms of background, in my printed notes, section chapter 2 has in it a complete just note for note copy of the text that I did in my 504 statistical mechanics class on the basic properties of Bose-Einstein condensates. So if you don't know about that, please review that, and I put the section numbers in the Teams chat. Okay, so let's talk about the basic ideas. So the idea is first of all, what is a quantum fluid? And quantum fluids are essentially fluids which are not solid, due to zero-point motion. So you might expect that as you cool things down, they become crystalline or some kind of solid, and that would be true. But the superfluids or the quantum fluids are the isotopes of helium-3 and helium-4. So these are, so basically in this course, we're going to deal with helium-3 and helium-4. And in fact, I'm not really going to say very much about helium-3, although it's interesting to do so. So let me just say that helium-3 is interesting because it is an example of a Fermi liquid. In other words, a strongly interacting Fermi system, strongly interacting Fermi gas. And a lot of the phenomenology of quasi-particles and so on was developed to study the normal state of helium-3. So a strongly Fermi gas in the normal state. And so this gave rise to a thing called the Lambda theory of Fermi liquids. And the other reason why we study helium-3 is because it forms a composite boson superfluid. At very low temperatures, and these low temperatures are basically in the millikelvin range. So the main point about helium-4. So helium-4 is a boson itself. And I didn't mention this, but I probably should have done. That helium-3 is of course a fermion, and so that's why they have very different characteristics. And so I'm going to just focus on helium-4. So it's a boson, and it undergoes a Bose-Einstein condensation. But when we talk about Bose-Einstein condensation, what we usually mean is ideal bosons. So this is for ideal bosons. So it's not an ideal boson. And so that means that the behavior is influenced by interactions. And we're going to see in later how to deal with those interactions using techniques from quantum field theory. So that's the theory of quantum fluids. Let's just quickly remind ourselves, when do quantum fluids become important? When do quantum effects become important? And the answer to that is basically what you learnt on your mother's knee, namely that if I have a box with a bunch of particles in it, so here's my particles in a box, and then what I do is I ask what is the uncertainty in the wave functions around those particles. So you can measure the uncertainty in the wave functions, if you will, the spread of the wave functions, by measuring something called the thermal de Broglie wavelength. And so if the thermal de Broglie wavelength around these particles is something like I'm drawing here, and this is really just a schematic. So the idea is that this smear is meant to represent the thermal de Broglie wavelength. And we get the thermal de Broglie wavelength by basically asking when is the kinetic energy of the particles roughly equal to kBt, and then we use the idea that there is a just like in de Broglie's wavelength, we just make the idea that there's a temperature-dependent wavelength defined through this criterion here, and this, of course, is the expectation value of p squared. And so what that ends up giving you is that the thermal de Broglie wavelength is h over 2n pi kb T, square rooted like that, and the so this is the wavelength that corresponds to the average momentum. So that's the thermal de Broglie wavelength. So how do you decide when quantum effects are important? So the quantum effects are going to be important when the thermal de Broglie wavelength is larger than the distance between the particles. So here you can see the distance between the particles. Let's call that distance L. So L equals the interparticle distance. And what is L? Well, the number of particles per unit volume is the number of particles per unit volume. So the volume per particle is equal to 1 over n, and that means the length per particle is equal to 1 over n to the 1/3 in three dimensions. And if you were in 2 dimensions, of course it would be different like that. And so then what you require is that for quantum effects to be important, what you need is that the thermal de Broglie wavelength should be greater than a number that scales like 1 over n to the 1/3. And so when you go and work that out, what you find then is that this is a temperature below a temperature which we'll call T quantum, and we can estimate that temperature. So that's going to be something like h bar squared over 2n pi kb times n to the 2/3. And if you put the numbers in for helium, what this gives you is that this temperature is about 5 degrees Kelvin, something like that. So that's when quantum effects become important, and then actually it turns out that this is actually quite interesting, because in fact helium 4 becomes a superfluid slightly below that at about 2 Kelvin. And so it's pretty consistent with this estimate. So let's then take a look then at the phase diagram.
I have a question.
Sure.
Is TQ significantly different for helium-3 versus helium-4?
It is different, yes.
Okay.
You can just work it out yourself. But you know, these are only estimates. Remember that this estimate is very crude, because we're just saying that the energy is just kinetic energy, and so we're ignoring interactions and all kinds of things like that. So the only place that the difference between helium-3 and helium-4 would come in is in the mass here. So it's not very different. Okay, it just depends on that isotopic difference.
Wouldn't the average momentum defining the thermal wavelength be different, since they have different distributions?
Well, not really. I mean, this estimate here we're just making some sort of classical estimate. So don't
okay. So we're not, yeah.
Yeah, so don't take these numbers too seriously or try to get them too accurately. We're just trying to guess, is the number 100 degrees Kelvin, or is it 5 or 2 or something like that. So we're just trying to get some idea. Okay, so let's have a look at the phase diagram of helium-4. So the axes of our phase diagram. Our temperature are up here and pressure over here. So this is in Kelvin, this is in atmospheres. And I'm going to put up here, say 25 atmospheres. And down here, 1 Kelvin, 2 Kelvin, 3 Kelvin, something like that. Okay, so that's the phase diagram. So let's have a look at the various phases here. So the first thing is that helium can be made to be a solid at 0 temperature, but you have to squish it with high pressure. And so there's a line that goes something like this, and above this line you have solid helium. So 25 atmospheres. And then, of course, if you have very low pressure, it will be a gas. So there's another line down here, which I'm probably not going to be able to draw very well to scale. And in this region here, what you have is gaseous helium. And then in between, you have liquid helium. So all of this here is liquid. And this phase here is called liquid helium-1. Actually, I said helium-1, but I meant liquid helium-2. And then this phase over here is liquid helium-1. And so this phase, the liquid helium-1 phase, is basically a regular liquid. The liquid helium-2 is a superfluid. And this line along here, this transition here is in fact a second order phase transition or continuous phase transition. All the other transitions on this curve. So here I'll just draw a few of them. These are first order transitions. Well, I actually ended up drawing all of them. There is a critical point out here, which we're not going to really focus on. And this line of transitions here is called the lambda line. So this transition between liquid helium-1 and helium-2 is called the lambda transition. And you can see that there actually isn't one lambda transition. There's a whole there's a whole range of lambda transitions depending on the pressure. So let's talk about why it's called a lambda transition. So if we go through the lambda transition, which is really quite fascinating, and we spend a bit of time talking about it in the phase transitions class, but we're not going to spend any time on it here. So again, what you plot here is the temperature, and now what I'm going to put on the vertical axis is the heat capacity in joules per gram per Kelvin, and somewhere along here. So this is about this is T lambda. So something like 2. What transition? What number are we going to use here? Well, something like 2. Let's 2.18 Kelvin. So that's this point over here. Okay, so we're looking somewhere down there. And why is it called a lambda transition? Well, if you had a regular second order phase transition, you would get a discontinuity. So that would be a regular second order transition. And when I say regular, what I mean is in the Ehrenfest sense. Ehrenfest classified transitions according to the order of discontinuities of the free energy. So if there's a discontinuity in the first derivative of the free energy, that's a first order transition. If it's discontinuous in the second derivative of the free energy, that would be a second order transition, and so on and so forth. So that was the understanding at the beginning of the century, and we now know that that is completely wrong. In fact, what happens is you get all sorts of other singularities happening at a second order phase transition, nothing to do with discontinuities. And so actually the way that this transition should look is different from what I've drawn here. So let me draw it like this. So what actually happens is that you get a curve that actually diverges to infinity and then comes down like that. And so the fact that it seems that the heat capacity diverges at T lambda, this gives this divergence is what you see in the modern theory of critical phenomena. So that's sort of how people understood things, and then very quickly they realized that actually it's not quite even true that it's diverging. So in fact, it's a bit more complicated than that. In fact, early on, it was thought that the heat capacity diverged logarithmically. And then later diverged as a power law, which is the usual case for critical phenomena. And then it turns out that even that's not correct. That actually what happens, actually it turns out to be a cusp. So it doesn't actually diverge at all. And so here's what we know is that the heat capacity actually goes like this, some background, which depends on whether you're above or below the lambda transition, and then something like this, B over alpha times T minus T lambda over T lambda raised to the power minus alpha minus 1. And this alpha turns out to be minus 0.013 plus or minus 0.003. And so what that means is that you have a cusp, and we know that this is true for T minus T lambda over T lambda, ranging from 10 to the minus 3 down to 10 to the minus 8. So this is the relative temperature difference from the critical point. And so what we have then is 5 decades of scaling. And this is one of the most accurate tests of the theory of critical phenomena. And to do that test, we had to go and do experiments in microgravity on the space shuttle, and that's it costs $50, $100 millions of our money, but it was worth it to know that the renormalization group still worked. All right, so that's the lambda transition. So now let's look at the properties of helium. So So what I want to do is I want to sort of walk you through what would happen as I took some helium, put it in the lab, and then lowered the temperature, and what would I see? And I see that somebody asked a question. Somebody asked a question: why is alpha negative? It should be positive to have a divergent heat capacity. Yes, you're right. And so it doesn't diverge. When I say a cusp, maybe you don't quite know what a cusp is. So what a cusp is this. Here's C and T. Let's zoom in to that region here. And then what I'm saying happens is that it actually goes like this and then like that. So it's still non-analytic, but it's non-analytic in this weird way. And the theory actually predicts that, so that's all good, but it's not the usual thing that you expect to see in critical phenomena where things literally do usually diverge. So in this case, it doesn't, and that's just a peculiarity of this particular transition. Okay, so hopefully that answers your question. Let's move on to what happens as you cool down helium 4. And before I go any further, let me also mention this. If you look on the web page for the course, you'll see that there is a movie page. Okay, and I've put there several movies, and one of them is the classic movie of the physics of helium 4. And that classic movie, you'll see it described there. It's a classic movie. I was given the movie by John Bardeen, and I had it converted into a digital format and got permission from the people who made the movie to post it on the internet. And so that's available on the class page. So, don't hang around listening to the class. Go and watch the movie. You'll see the beautiful experiments that are shown there. They're really quite stunning, and so it's the best way to see how fantastic superfluids really are. Okay, so go and see the movie page. Okay, so what happens is this: let's suppose you're above T lambda, and you're reducing the temperature. So what will you see? So what, of course, you'll see as you as you as you cool down, and what you will see is that the helium will boil. So you're keeping this at constant pressure. So the helium is going to boil. So it's in equilibrium with its vapor. And what's happening is you're pumping on helium. So you're pumping away gas, and because you're pumping away gas, what happens is liquid turns into gas, to keep the equilibrium vapor pressure constant. And so what will happen is you'll get local hot spots in the fluid. They create a sufficient vapor pressure to overcome hydrostatic pressure. And so that's called a bubble. That's what a bubble is. So it's just a local hotspot, and because it's a bubble, it has lower density. And so what that means is it rises if you're in a gravitational field. So everything I just described is just the standard description of boiling, nothing special, just boiling of water will do this. Okay, so who cares? Well, what's fantastic is that when we get down to the lambda point, the boiling stops. If I remember correctly, in the movie, you actually get to see this. You see the thing fizzing away like Coca-Cola or something like this, and all of a sudden, just suddenly stops like that. And so, so the question is, why? Why does that happen? So you might think, well, it's impossible. How can this happen? You can't stop boiling. So the only thing that could possibly explain this is you might say, well, the whole phenomenon of boiling requires there to be these local hotspots in the liquid. So maybe there's no hotspots. If there's no hotspots, then there's no boiling. So the answer is no hotspots. So if there's no hotspots, how can that happen? Well, it's impossible to happen. So what you might say is, well, suppose I try to make a local thermal fluctuation. If that heat immediately gets conducted away, then you won't be able to get a local hotspot, because the whole point of a hotspot is it is a spot. It is localized. So you might guess that no hotspots, then that would mean that there is a large, perhaps infinite, thermal conductivity. So something like that might seem to be happening. So let's just so here we are. I just want to make sure that you know exactly where we are on the phase diagram. So here's the phase diagram, and what we're doing is we're going down this line like that. Okay, I want to make sure that you understand that. And because we're going on that line, that's why we are on this equilibrium between liquid and gas. So let me just make sure that all of you are completely on board with this. This is the liquid gas coexistence. So that's what I was using to make these statements. Okay, so now we've got something strange there. So what's the next thing that we see? Well, the next thing that we see is we can do an experiment to look at how the fluid flows. And the experiment that you do, it looks like this. So let me try to draw it first. I'm not very good at the drawing, so let me do my best here. So something like this. All right, now let me put in a plunger over here. And then in this part here, this is a narrow constriction. And in the movie, what they use is a substance called jeweler's rouge, which is, I don't really know what it is. It's something kind of like, I don't know, kind of like lipstick or some kind of paste, but it's got very, very fine pores. And if you put it there, the fluid has to go through it. So it's a way to make a very a narrow constriction. And then the other thing that I need over here is I need another one of these. these this thing like this. I forgot that. And then let's put in the fluid. Fluids are always blue, so here's the fluid, like so. And the thing that you might want to ask is this: if I'm pushing a fluid, through a pipe like this, what you would expect is that there should be a higher pressure on the left and on the right as you're pushing the fluid through this constriction. But what you find, in fact, is that the height of the pressure here is the same. So this thing is called a manometer, as I hope you know. And so instead of being different pressures, different heights of the fluid there, what happens is they actually have the same height. And so you've got this very strange situation that what you can do is you can push helium 2 through this capillary. That's the name for this thing here, capillary. It's another word for a narrow constriction, and you can push it through the capillary with no pressure drop. Unlike with regular fluids. In a regular fluid, if you want it to flow, you need to have a pressure drop to make it flow, but this will flow without that. So usually you have some viscosity. You have viscous forces that need to be overcome. To move the fluid through a pipe. But in this case, you don't. So that suggests the bizarre idea that the shear viscosity is equal to 0. So that's the idea of a superfluid. So we'll see that is there is some sense in which this is true, but I want to make two caveats. So there's two experimental caveats to this observation. So that the first one is that the velocity must be less than some critical velocity. And we'll talk a little bit about what that critical velocity actually is and what determines it. So that's one experimental caveat. The other experimental caveat is what's called the Andronikashvili experiment. Andronikashvili. How many L's? One, I suppose. One is the Andronikashvili experiment. So what is that? What is the Andronikashvili experiment? So what he did was he took a torsional oscillator. So this is a set of rotating disks. which are immersed in helium-2, and so you make a kind of a torsional pendulum. And this thing slows down. So you might think, wow, why does it slow down? If a fluid has no viscosity, it shouldn't slow down. So that's the question, and the resolution of this is what is called the two-fluid model. So in the two-fluid model, what you say is there's no way to explain this because there's a fluid that can flow without viscosity, and so we'll call that the superfluid component. So the idea is helium-2 has got two components. Superfluid component, which flows without drag, let's say. And then the normal fluid component, which does have drag. And so the idea is that that in the geometry of the Andronikashvili experiment, there's still drag from the normal fluid. But in the flow through the capillary, only the superfluid gets through the small constrictions. So you can have both of these things can be true, and so the idea is that you have the at every point in space what you have is a normal fluid velocity Vn of r. You have a normal fluid density rho n, which I suppose depends on r in principle, and also the temperature. And then you also have the superfluid velocity, and you have the superfluid density, which depends on space and temperature. So these things are the velocities, and this is the density. So this is normal and superfluid. And then the idea is that the density at any point in space, the thing that you measure, is the sum of the density of the normal fluid and the density of the superfluid, like so. And the two velocity components obey different equations of motion.
Hi, Nigel. I had a question.
Sure. Let me just finish the sentence and then I'll take your question.
Sure.
Okay, so let me just finish this and then I will take your question. So the question that you probably should be asking is, what does this obviously fictitious phenomenological model mean in real mechanistic atomic terms, atomistic terms? And we'll get to that. Okay, so who had a question?
Hi, I had a question.
Yes, hi, go ahead, Siddharth.
When you say in a flow through the capillary, only superfluid gets through them small constrictions, does that imply that in one end you would have superfluid plus the normal fluid, and in the other half you just have superfluid?
Or you'd have more of it, yes. That's right. And you'll get, and in the homework, I don't know if I'll give you this in the homework because I'll try to reduce the homework load on people because it's, you know, virtual and so on. Maybe I'll add it as an optional question. I'm not sure, but yes, that's exactly right, and that leads to a very interesting effect, which is called the fountain effect.
Okay, thank you so much.
Yep, yep, you're absolutely right. It's a good. It's a good question. So what does this mean? Oh, what? Yep.
I have a follow-up question.
Hmm.
So can't you prove or disprove this model by just pushing the plunger in that experiment all the way and see if, you know, if the
you can
do that without resistance?
Yep, you can. There's lots and lots of validation of this model. Yeah. So let's talk about. So what does it mean in mechanistic terms? So the first thing I want to say is that these two, the two components are not literally physical fluids. And in particular, the main thing I want to emphasize, in particular, they do not transfer momentum between themselves. They do not transfer momentum between the normal and superfluid components. So the idea is you just go to a point in space, and at that point in space, you can regard it as if there are these two components with two separate velocity fields at that point. Now, of course, when we talk about the points, when we talk about fluid dynamics, as you know from my stat mech class, we're talking about a coarse-grained description of a system already much larger than the mean free path. And so these are sort of effective phenomenological descriptions. And when we talk about these things, we're neglecting a momentum transfer between them. And that's in anything you'll read in textbooks will always talk about that. But this assumption actually breaks down when you have turbulent superfluid helium. And if you want to ask me questions about that in office hour or something like that, I can talk about it for ad nauseam. So this is something super interesting. So let's go and talk now about what the equations are that describe the superflow. So the question that we have now is, so the normal component is Navier-Stokes, but what about the superfluid? And so the answer is that the superflow, that's what we tend to call it, superfluid flow, superflow. The superflow is irrotational. Now, I realize that most of you have not had much background in fluid mechanics, but let's remind ourselves what irrotational means. Irrotational means that if I take the curl, then I get 0. So, so that's the idea. So why do we think that why would that help? So we can see that this would explain superfluidity as follows. So let's talk now about how you would measure the viscous drag on a fluid. So let's suppose that you start off with a wall. Oh, I made a cardinal sin, didn't I? I made the wall be blue, even though the fluid's supposed to be blue. Okay, well, we'll have a green fluid this time. Okay, so here's a fluid. We're going to set up axes. So this is the x direction. This is the z direction. And if you're pushing the fluid from left to right, what would you expect the fluid to be doing? Well, so here is the fluid. There's the velocity field, v in the x direction as a function of z. And what you would expect is that if it's got a velocity vector out here away from the wall, as I get closer and closer to the wall, the fluid velocity gets smaller and smaller because there's a no-slip boundary condition at the wall. And so what you would expect then is that the fluid velocity would be something like this. And so that's how you would expect the fluid velocity to vary in space, and this behavior here, there's a no-slip boundary condition at the wall. So this is what you would expect as for a regular fluid. Okay, so that's your intuitive picture, and the reason for this the progression of velocity here is due to the fact that you have viscous drag. So there's a no-slip boundary condition, and that kind of reflects the viscous drag. And as you go further and further away from the wall, that viscous drag becomes less and less as you go further and further away from the wall. So that's what you would expect. So that viscous drag gives you a velocity gradient in the fluid. So that's sort of fluid mechanics 101. So how would you quantify that? So what you would do then is you would say, well, what is the force on the wall? Exerted by the flowing fluid. So as the fluid goes past, it's dragging the wall with it, or it would like to, and you have to hold the wall steady so it doesn't move. And so what you would expect is that force is going to depend on the area. So we'll just divide by the area, and that's going to be proportional to how big is this velocity gradient. So it's going to depend on dvx by dz. Obviously, if the gradient is very steep, then that means that as the fluid flows through, it will exert a very sharp force on the wall. If the gradient is very small at all, it'll not be much at all. So the force is going to be proportional to that, and so that means that there must be a constant of proportionality that goes in here, and that constant of proportionality is known as the shear viscosity. And then the other thing you might say is, well, why do we assume that it's proportional just to the first gradient? Maybe there are higher order terms here, and there may well be higher order terms, and we're going to neglect them because this is what we expect from the point of view of linear response theory. Linear response theory says that if you apply a force, the response of the fluid, in this case the gradient that is induced, is proportional to the force that you applied. Okay, so this is what you would expect for a normal fluid. So now the question is, what happens if you have a superfluid? So if that's true, then what we would have is curl Vs is equal to 0. So we would have that dVx by dz minus dVz of x by dx is equal to 0. That's the one of the components of curl. But we know that Vz, V in the z direction, is equal to 0 because the fluid is just flowing in the horizontal direction. And so that then means that dVx by dz has to be equal to 0 as well. And so that then says that the force is equal to 0. And so that says that if I have an irrotational fluid, and I'm going to add in here the caveat that it is a laminar irrotational fluid. Irrotational laminar fluid will seem to have no drag. Notice that I didn't say that the viscosity was equal to 0, which is what people think. It's that it has no drag. So note that the force per unit area is equal to 0, and that's not the same thing. That's not the same thing as saying that the shear viscosity is equal to 0. But the effect is the same. You get a flow without drag, and you might say what happened to the normal fluid and the answer is simply that the viscous forces in the fine capillary tube caused the normal fluid to not go through, but the Vs could flow through with no difficulty. And in the Andronikashvili experiment, well, what's going to happen is there's going to be dissipation in the normal fluid because it cannot be simultaneously at rest with respect to the walls of the container and the rotating disks. And when I use this symbol here, that symbol means because. Okay, so that's the that's the Superflow experiment. So let's talk about the fountain effect. So the next thing I want to talk about is what's my numbering scheme here? 1, 2, 3. We'll call this 4 then, I guess. So this is a very spectacular effect. This is what happens when a superfluid can balance pressure, balances pressure difference with a temperature difference. And the basic cause of this will in fact turn out to be pretty much the same thing as the superfluidity that we talked about. So let me just show you what is the setup for this this experiment. So this is the following. So let me try to draw this. So something like this. We're going to have a fine capillary tube in here, and then I have the fluid. I'll remember to draw it in blue this time. So there's the superfluid like that, and you can see that there's a pressure and temperature here on the right hand side, but on the left hand side it's higher, and so therefore it has a higher pressure, so P plus delta P. And then what I didn't tell you is that it also has a higher temperature. So in the middle here is a coil, which in the experiments is something called a nichrome ribbon, and this heats the fluid up, and so it's at a temperature T plus delta T. And there's a height difference that you can see here. And so the pressure drop, of course, is going to just be just the density times gravity times the height difference delta Z, and what you find in the thermomechanical effect is that the pressure drop is related to the temperature drop by an amount that depends on the entropy of the helium-2. So this is the density, this is the entropy per unit mass of helium-2. And so this should be, this is a true statement, and in the homework you can you'll get an opportunity to think about how to derive this and see where it comes from. But for now, I just want to point out a very surprising thing. This is surprising because we thought that helium-2 had an infinite thermal conductivity. And we knew that because of the no boiling that we observed. Okay, so at one point we're saying that the temperature differences immediately get spread out because you've got this infinite thermal conductivity, but in this situation, and the one shown over here, that doesn't happen. And so if that's not happening, then how can we reconcile these two things? So we can reconcile this thing is sometimes called the fountain effect, and you'll see in the movie why. So we can reconcile the fountain effect with the no boiling, if we make the ludicrous assumption that it only conducts heat when the normal fluid can flow. So the thing that's special here is that we have this fine capillary. And because we have the fine capillary, we know that the normal fluid can't flow. We know that from our picture of the two-fluid model. So what this then tells us is that that this implies that the superfluid component, when it flows, doesn't transfer heat and doesn't transfer entropy. So this implies a kind of mad implication, namely that the superfluid component moves without entropy transfer. And so therefore, that if that's true, that implies that superflow is thermodynamically reversible. So if that's true, then it also says something else that's surprising. It says that only if the normal component flows, does heat get transferred. And so that's a kind of advection of heat. So that's called advection. But what that means then is that the flow of heat is limited by the viscosity. So there should be some relationship between that, and so another corollary of this is that let's suppose that I in a situation when there is no net mass transfer in a temperature gradient, then that means that you must get a counterflow. So let me just explain that because it's not obvious from the words. So here's the picture. So let's suppose that I have a closed system like this. So it's closed, and inside here is the fluid. And now let's suppose that I put in my nichrome ribbon to heat things up. Then what it says is I'm going to get something very strange. So this end here is hot, and this end here is cold from this picture. And so what's going to happen is the normal fluid is going to flow in the usual direction from hot to cold, and that means that there must then, because there's no net mass transfer, what that means is the superfluid component has to go in the opposite direction in order that there is no net mass transfer. So this is called a counterflow. So the fluid flows in one direction, and both all of these phenomena indeed occur. So it's a very puzzling, strange material, and we want to understand why it behaves like this. So the basic question is why does helium-4, why does helium-2 have these properties? So the basic answer is that it comes from Bose-Einstein condensation. So the basic answer is that the superfluid component is a form of a Bose-Einstein condensate. And what we'll see then is that means that because you have a Bose-Einstein condensate, everything is condensed into the ground state. That's what Bose-Einstein condensation is. And so basically what that means then is that if everything is in the same state, then there's no entropy, because the entropy is the logarithm of the number of quantum states. So if there's only one quantum state, so if you have macroscopic occupation of a quantum state, of a single quantum state, that means there is no entropy. And so that helps us to understand the effect. And the other thing is that if you have a single quantum state, with its own wave function, the superfluid velocity is proportional to the gradient of the phase of the wave function. And I'm going to explain that to you next lecture. But the main thing is that because the superfluid velocity is proportional to the gradient of the scalar, the phase of the wave function, that automatically means that curl of Vs is equal to 0. So this idea that the superfluid is a form of Bose-Einstein condensate seems to explain these ideas. And so you might say, well, what about the normal fluid? What about the normal component? And the answer there is that this is the fluid formed by the gas of elementary excitations. Above the ground state. So if you had an ideal gas of bosons, you know that they macroscopically occupy the ground state, and then there are excited states above that ground state. And so those excited states have multiple quantum states, so they carry entropy, and they flow. The excitations, if you have an interacting system, will collide and will transfer momentum. And so in an interacting system, the excitations will collide, transfer momentum, get a shear viscosity through collisions, and so they'll behave like a normal fluid. And so so basically the idea then is that the two fluid model which was originally phenomenological can be interpreted in light of Bose-Einstein condensation. So there's a problem though, because BEC is for ideal bosons and helium-4 are strongly interacting bosons. So next lecture, we'll talk about how we take into account the strong interactions, or at least in principle. We'll talk about what that means and how we can kind of quantify or extend Bose-Einstein condensation to the realm of strongly interacting quantum fluids. Okay, so I'm going to stop there. So let me turn off the recording, and then I'll be happy to take your questions.